For our next talk, we'll move on to Amnon Ptashek, who is the Technical Director of Allotrope, who will give us a tour de force of SHACL.
Hi, hello everybody. In today's presentation, we will describe the construction of Allotrope data model with shape constraint language to describe, validate, and achieve data interoperability. So let's start with motivation for SHACL. Linked data technologies were originally designed to publish data on the web, enrich it semantically, connect heterogeneous data set, and enable better information retrieval. The attention of linked data ontologies and control vocabulary is to ensure interoperability. It is not about the data restriction. They are not about data constraining. Ontologies help to infer, draw conclusions, and view the information in an extensive context. They were designed under open world assumption, which means what is not known to be true is simple unknown. Under open world assumption, what is not known to be true is simply unknown. Under closed world assumption, what is not known to be true must be false. SHACL covers data validation in a closed world. Open world assumption applies when a system has incomplete information, meaning information can be added later. Closed world assumption apply when the system has complete information, which means the information that we have is everything. In addition, closed world assumption assume the uniqueness of names to prevent ambiguities. So what does it mean for us, open world assumption versus closed world assumption? Let's assume that we define that the laboratory result record must include equipment ID. Under an open world assumption, if the result record is missing equipment ID, we cannot declare that the record is invalid. We can say that the equipment ID is missing. In a closed world, we have complete information about our system. Therefore, under closed world assumption, we can declare that the record is invalid. SHACL covers data validation in a closed world. So now that we understand the motivation for SHACL, let's dive into the SHACL specification according to the W3C documentation. The SHACL shape constraint language is a language for validating and describing RDF graph. It became an official W3C recommendation in 2017. And why do we need to formalize the description? For content producers, they can get clear guidelines. The content structure is unified and interoperable, and content distribution can be associated with its structure. On the other end, for content consumer, why do we need to formalize validation? They can get clear guidelines on the expected structure. Content consumer can verify it prior to processing, and expected content structure is unified and interoperable. The specification is divided into SHACL SPARQL, which adds advanced feature of SPARQL-based constraint, and we are not going to discuss it today. We are going to focus on SHACL core. SHACL core consists of frequently needed features for the representation of shapes, constraint, and targets. Again, shape, constraint, and target. And remember those icons, we are going to use them extensively in the following presentation. So let's start. A shape graph is an RDF graph that contains shape. So we have an RDF graph that contains shapes, and we have the data graph, which is an RDF graph that contains the data to be validated. So we have the shapes. This is the SHACL shape file. And we have the data graph, which is a graph to be validated. Now let's go and start defining the components of a data graph. Focus node is an RDF term that is validated against a shape. Practically, a focus node is the focus for validation by the shape. A shape determines how to validate a focus node based on its value of properties and other characteristics. So let's see, we have a shape, we have the data graph to be validated, and we are focusing on a node to be validated by the shapes. So let's continue with our definitions. The SHACL core language defines two types of shapes. The first one is called node shapes, those shapes about the focus node itself, and again, they are called node shapes. So we have the shape, and we have the focus node, and the shape about the focus node itself is called node shapes. And the other one is shapes about the value of a particular property or path for the focus node is called property shape. So we have the focus node, and we have a path coming out of the focus node, and those shapes are called property shapes. So again, let's summarize for now. We have property shapes and we have node shapes, and node shapes about the focus node itself, and property shapes is about the property or the path that is coming out from the focus node. So let's continue. Now we are diving into the shape. A shape is a collection of constraint components and targets. The constraint can declare their severity, info, a non-critical informative message, warning, a non-critical constraint violation indicating a warning, and violation, a constraint violation. So we have info, warning, and violation. And we'll see later on when we'll operate the SHACL validator, we'll see a violation coming out in the validation report. So let's now try to build the shape. Constraint component determines how to validate a node. So we have a shape and we have constraint components. And shapes can declare constraints using parameters of constraint components. So we have a shape, we have constraint components, and we have their parameters. And now we have target declarations. Targets specify which nodes in the data graph must conform to the shape. Practically, the target declaration specifies the selection of the target nodes for validation by the shapes. So let's summarize again. We have the shapes, we have the constraint component, we have the parameters, and then we have within the shape a target declaration that specifies the selection of target nodes for the shapes. So there are several types of target declaration that specify the node that must be validated against the shape. So let's look at the type of target declaration. We have target node directly point to a node. So we can have a target declaration that directly point to a node. We have target class. So we can specify a class of node that have it for a given type. So the target declaration is a target class. The third one is target subject of all subject nodes that have a given property, subject, predicate, object. So we have the subject, all the nodes that are subject node that have for a given property P. So in this case, those two nodes have the property P, so they are the target for this shape for validation. And the last one is target object of, subject, predicate, object. So all object node that have a given property. So in this case, we have two nodes that for this given property that are target for this shape. And our last definition, and we conclude our definition, is the value node. And we have to understand this value node, so we'll understand later on the exercise and how those ADMs and the SHACL shape works. The validator of most constraint components use the concept of value node, which defines as follows. The value node is the node where the constraint components are applied to. So again, let's summarize. We have the shapes, we have the constraint component, we have the parameter of constraint components, we select our targets, and now we have the value nodes where we apply the constraint. Again, where we apply the constraint, and not necessarily the target node or the focus node is the same node that we applied the constraint. So let's see the different cases. In the case of a node shape, it's a node shape. So a node shape, if you remember, the focus node is the node that the shape is to be validated against. So it's a node shape, it's about the node itself. So the focus node is becoming the value node. So for node shape, the value node are the individual focus node. So the focus node, our focus in the graph, is becoming the value node. And the value node is where we apply the constraint. On the other end, for property shapes with a value of path P, this is the path, the value node are the set of nodes in the data graph that can be reached from the focus node. So we have a focus node. Again, the focus node is where we apply the shape, but the constraint will be applied to the value node. So in this graph, two value nodes can be reached with the path P from the focus node. So the constraint will be applied to the value nodes. So let's summarize the validation process. We start with a data graph. This is the data graph. That's where we start. We apply targets to select focus node, and practically the target declaration specifies the selection of the target node for validation for the shape. And we saw 4 types of target declarations. So we select the target for validation by the shapes. Filters are used to eliminate some of the focus node. We can use filters, and we didn't discuss filter in this presentation because this is part of the advanced SHACL SPARQL. And we apply the constraint components to the value node and use them to produce a validation report. So if you remember, the constraint components are applied to the value nodes, and we had 2 types of value node. One where it's a node shape, where the value node is the focus node, and one when it's a property shape, so the value node are those nodes that can be reached from the focus node. And that's conclude our definitions. Last but not least, for a syntactic validation of a SHACL shape graph, W3C provide a SHACL shape graph called SHACL in SHACL, pronounced SHACL in SHACL, that can be used to validate other SHACL shape graph using a subset of syntax rule. So we have the SHACL in SHACL that provided by W3C, and we have our own SHACL shape file, and we want to perform syntactic validation. So we are using this SHACL in SHACL for validating our shape files. And now that we are expert on the theory of SHACL, we can exercise on a daily life use case. And for daily life use case, we will validate the selection of a tire for a 1950 Studebaker Champion, our old car, base model 1950. So let's look at the SHACL. It's a partial content of a shape file in Turtle syntax on the left side. And on the right side, we have the data graph to be validated. So let's try to understand, first of all, the data graph. We have Studebaker, which is the car maker, manufacture a model called Champion, and there are several sub-models of Champion, base, luxury, standard. This is a base model, year 1950. And we wanted to validate the selection of a tire for this car. And we have here 2 shapes out of the shape file. The top one is a node shape, and also the bottom one is a node shape. And let's look at the declaration. Make shape, the top one is a make shape, is a node shape, and the bottom one is model shape, is a node shape. So 2 node shapes. So we start with a target declaration. So the first one will start from the top. The target class is make. Let's look at the data graph. Who is the target class for the make? So Studebaker is a type make. So the target node for the top shape is Studebaker. And let's look at the bottom shape. The bottom shape, the target class is model. So who is in the data graph is type of model, so Champion. So Champion is becoming the target class for the bottom shape. And practically the target declaration specified the selection of the target node for validation by the shape. So now that we have the target declaration, we have to find our focus node. Practically a focus node is the focus for validation by the shape, and shapes about the focus node itself are called node shape. So since it's a node shape, it's a shape about the node itself. So the target node is becoming the focus node for the top shape, and also for the bottom shape, champion, which was the target node, is becoming the focus node. And again, because this is a node shape and it's a shape about the node itself. We'll see later on property shapes. So now we have to select our value node. And value node, practically value node is a node where the constraint components are applied to. So since it's a node shape, for node shape, the value nodes are the individual focus node. So Studebaker for the top shape was the target. It's becoming the focus for validation. And since it's a node shape, it's becoming also the value node where we will apply the constraint components. So let's look at the constraint component that we will apply for Studebaker as the value node. There are two constraint components that we can see here. The first one is not, negation, and the second one is class. And practically it says that the value node Studebaker, shall not satisfy the type model, And practically it's to avoid a confusion between the car maker and the car model. Sometimes people are mixing between the car model and the car maker. So this is type of negation. And that's conclude our constraints for the node shape. And we continue with property shapes. And we have here three property shapes. One at the top, property shape, and two at the bottom shape. We have two property shape embedded within the shapes, and shapes about the value of a particular property or path for the focus node are called property shapes. So let's remind you again that the focus node for the top shape is Studebaker, and for the bottom shape is champion. So let's start with the top shape. So the property shape is the path manufacturer. So Studebaker as the path manufacturer to champion. So, and the champion in the bottom shape, which is the focus from the bottom shape, has two property shapes. One submodel to base, and 1 year 1950. So let's start from the top and find the value node where we apply the constraint components. So for the top shape, if you remember, practically the value node is the node where the constraint components are applied to. So the value nodes for property shape are those nodes that can be reached with a path P from the focus node. So let's look here at the top shape. The property is manufacturer. So Studebaker as a path manufacturer, and the value node that can be reached from the focus node to the value node is champion. So champion is becoming the value node for this property shape. So we can apply the constraint components on champion. And let's look at the constraint components. We have two constraints components. One is class model, and the second one is minimum count one. The value node champion shall exist, satisfy the type model. And indeed, champion is of type model. So this is the implementation of a value node in a case of property shape. And now let's do the same thing for the bottom shape. And we'll start with the property submodel. So for the bottom shape, champion is the focus node. Champion was the focus node. And then we need to find the path for the value node. So the path that can be reached for submodel is the base submodel. And so base is becoming the value node. And we apply, again, the constraint components on the value node. So two constraints component. One is the minimum cardinality, minimum count is 1, and the data type is string. The data type is string, which translates to a value node, which is base shall exist and satisfy the type string. So it satisfied the type string. And let's go to the next property shape. Again, the focus node is champion. For the bottom shape, it's champion, and the path is year. And we see that the value node is 1950, and the data type is year, which translates to the value node shall exist 1950 and satisfy the data type year. So now that we are expert on a daily life use case, we can utilize SHACL to describe and validate ADMs, Allotrope Data Model. So first of all, where can we find the ADM, the Allotrope Data Model? Within our community GitLab, under the ADM repository, we see several subfolders, and we see diagram, manifest, queries. We see the shape subfolder. We look into this shape subfolder, and we see several other use case and techniques. Each one is within its own folder. So we have balance, BGA, bulk density, calibration, cell counting, and so on and so on. So let's dive into one of the folders. We can find the shape files, and within the shape files, we found node shapes and property shapes, and we will exercise today ADM validation on a conductivity shape. And out of the conductivity shape, we will pick one node shape. And how do I know that it's a node shape? AFS 615 is a node shape. That's the declaration. And let's look at this node shape. So this node shape, first of all, we start with target declaration for the selection of focus node for the shape. So the target declaration is target class AFR 1587, AFR 1587. What is AFR 1587? Very simple. We look on our Perl server and we see that AFR 1587 is conductivity. So the target class for this shape is type conductivity, which translates to a line item within our conductivity tabular model. And this node shape includes three property shapes, one embedded, and two linked property shapes external to this node shape. So let's focus on the embedded one. The embedded one is a property with a path type. So we apply the constraint components on the value node, and it has three constraint components: maximum count 1, minimum count 1, and a node kind of a resource, IRI, which means that connectivity node, the conductivity node, remember the target class was conductivity, is of a single type of a resource, IRI, which translates to a single key value pair in our conductivity measurement tabular model. And now let's look at the additional property. We didn't mention it earlier. The property message is used to associate a human-friendly message with a shape. Practically, a SHACL processor, like a SHACL validator, a SHACL processor can include the message within the result in the validation report if there is a violation that affects that shape. And later on, we will see a violation of a shape, and we'll see how the message within the shape is forwarded to the validation report. So now let's look at the other two property shapes that are external and linked to this node shape. The first one is property shape with a path numeric value. So we apply the constraint component on the value node. If you remember, the value node are the set of nodes that can be reached with a path P from the focus node. And we see that the constraint components, we have four constraint components: data type double, the maximum count is 1, the minimum count is 1, which means the cardinality is exactly 1, and the node kind is a literal. This time the node type is a literal, which means it translates to electrical connectivity must have exactly one numeric value of type double. And now let's look at the property shape on the unit. So the path for this property shape is unit. And on the value node, there are two constraints that are applied. One is as value Siemens per meter, and the other constraint is a node kind of a resource, IRI, which translates to electrical connectivity must have exactly 1 unit of Siemens per meter. So now that we are expert on the SHACL theory and we're expert on how to utilize SHACL file and ADM, we can see our SHACL validator. The SHACL validator evaluates conformance of the ADM data instance with a set of constraints in the associated shape. So we have the SHACL validator, and we have 3 inputs. We have the data instance, the SHACL file, and the vocabulary, which is optional. Again, the data instance to be validated, the SHACL shapefile, and the vocabulary input, which is optional. And it produces in its output a validation report, which confirms true or false, pass or not pass. So we will output a validation report with conformance of true or false. So let's start our exercise with a SHACL shape violation example, where we input a data instance to be validated with 2 different serial numbers. Yes, we have here 2 different serial number, equipment serial number, and we are going to violate a property shape that with a path that to the value node that mandate that the type is string and the cardinality is 1. Maximum count 1, minimum count 1, which means the cardinality is exactly 1 and the data type is string. And we see here a message, equipment serial number must have exactly 1 value of type string. And we'll see that once it will be violated, we'll see what happened to the validation report. So let's turn it on and let's produce a validation report. And we see that conforms equal false. So the validation failed, and we see a violation. And we see here the result severity is violation. If you remember, it was info warning violation. So the severity is violation. The related message in the property shape was forwarded to the validation report. Equipment serial number must have exactly 1 value of type string. And we see also the constraint component that was violated. Source constraint component, maximum count constraint component. So the cardinality of the equipment serial number, the number of equipment serial numbers was violated. Let's fix this violation. We will erase the one of the serial numbers, and we have a shape with a single serial number. Now we are within the right cardinality. We will turn the validator on, and it will produce a validation report. This time confirms equal true, no violation, everything is correct, it passed. Where can we find the Allotrope SHACL validator? On our community GitLab under the SHACL validator repository. If we look into it, we see different type of installation for the SHACL validator. And thank you for your attention.
Great, thank you, Amnon. Unfortunately, we're running a little short on time, so I don't think we can take any questions for today, but the slides will be sent out, and certainly you can reach out to Amnon. He'd be more than happy to walk you through any of the concepts. So thank you, everyone. Thank you, Amnon.
Thank you.